In the early universe, the standard cosmology have several problems, and to solve the such a problem like the blackness and the horizon problem, usually is the cosmic implications introduces, which is the extremely rapid expansions of the universe. In the blackness problem, from the Boltzmann equations, the curvature term should be the near the blood in the early approach, and in the horizon problem, um, to explain the CMB spectrum, the correlation between the temperature, the Hubble horizon term, 1 over the AH should be large in the early approach, and this requires that the population's expansion with this 60-fold border scale factor. And usually the implementation model can be classified the form of the scalar potential in Platon fields introduces, and we can calculate the e-fold expansion and the several quantity like as the power spectrum index and T for the scalar and the tensor to scalarity R. These two quantities are observable in the from the CMB or other measurement. So in this video, I will talk about the several implementations model as an overview. So here's a review on the scalar field dynamics. This is action of the scalar field in the expanding universe. So if we insert the FLRW metric here, the equational motions are following, and the energy density and the pressure satisfied this one from the stress tensor. And in the slower condition, the kinetic term is just smaller than compared with the potential term. So the energy density low and the pressure has relations of the opposite sign. And one can define the two parameters to represent the slow low epsilon and eta. Eta represents the slow changes of the epsilon dot. And after the implementations, the Platon fields eventually decay to the standard model, which is called the lating. And this Platon field pies oscillates, so the rapid reproductions with the parametric resonance can be possible. This is called the preheating. And such lating occurs at some specific temperatures, so when the decay rate via this Lagrangian coupling between the Platon fields, and these Hubble parameters are same at that lating temperature. And usually the primordial perturbations generated from the cosmic impulsion, and this makes the large scale structure. The Platon field can be decomposed with the background part and the fluctuation part. And this fluctuation part makes the perturbation in each mode. The scalar curvature perturbation R gives the scalar power spectrum index NS, and the tensor mode with the matrix Hij. This makes the gravitational indices from the cosmic impulsion. And one can evaluate the tensor to scalarity R. This NSR can be observed by the measurement. The value of NS is near the 0.296, and the tensor to scalarity R is less than the 0.036 in the some 1 or 2 sigma level. And depending on the implantation model, the potential form of the Platon field is the parameter space over this NSRs are determined so that we can test whether implantation model is still valid or excluded. So there are several models. Here's a list, like as the chaotic, R-square, hilltop, Paolo, Higgs implantation, natural implantation, Strobanski, alpha tract hybrids, and the supersymmetry introduces. And we will talk about such a several model and why such a models are introduced such a motivation thing. So first, I will talk about the well-known example. So first one is the chaotic implantations. In the chaotic implantations, the form is such a pi of q. The initial condition is random here, and in this case the potential is very steep. So this is how to explain the slow rule, but the large energy density makes the large Hubble parameters by the Boltzmann equation. This makes the Hubble friction is large. So slower is possible, even though the potential slope is very slope. We can evaluate the slower parameter epsilon and eta, and from that, the formula requires that the Bill scale pi should be larger than the Planck mass to realize the slow condition. So the such a chaotic implantations is the case of the super Planckian. Some weird scale rather than the Planck scale is necessary. Also, one can calculate the power spectrum index and as the tensor to scalarity R as a functions of the such a Q, and the some of the potential forms are largely excluded, like pi 4, pi 3, pi 2, because this gives the too large R, the tensor to scalarity compares with observed value. R is less than the 0.036. So there are other models also introduces hilltop implantation. In this case, the Bill scale is scaled by some specific parameter lambda. This is smaller than the Planck mass scale. The hilltop implantation potential has the following form. The pi starts to the top and it moves to the hill with some specific bob. This hilltop implantations are still valid because this can give the relatively small tensor to scalarity R. Also, there is a natural implantation. In this case, the shift symmetry from the non-perturbative impacts the adoptives, like as axion physics, such as shift symmetry is surpassed by the quantum loop correction. So the such a degenerate vacuum state it can be possible. So this can maintain the blindness through the potential. And the other model is hybrid inflations by introducing the second scalar chi. We need to maintain the large VGO, the constant term, so that the energy density is still large enough, and the large Hubble frictions can make the slow roll, but we want to make the small scale of the pi, not the super Planckian, and the mass coefficients of the second scalar chi can be the negative or positive, depending on the pi build is the whether it's larger than the critical build value, and such a chi contribution depending on the situations of the critical build. These contributions can cancel this constant term at the end of the implantation. So the when the pi build is larger than the critical build in the early approach, there is no contribution, so the large visual is make the slow roll condition, but below the such a critical build, chi becomes massive, and the such as low roll becomes Andes, and the implications also finishes. Now I want to talk about some modern model. The well-known example is just Strobanski model with exponent form, exponential of the minus this form. Also, the scale of the pi is relatively smaller than the Planck scale, but it is cube factor. In the large pi, there is a plateau. The flatness of the potential. So in this stage, the impulsion occurs, and eventually the impulsion finishes. There are several dedicated model to generate this Strobanski impulsion form. One is the Higgs impulsion. In Higgs, the scalar field Higgs is coupled to the gravity. This the Riemann curvature form. So this is the type of the scalar tensor theory. In the Jordan frames, the f of r, the functions of the Riemann curvature tensor is not equal to the r. Just r is the same with the Hilbert action of the general relativity theory. But if we transform by the conformal symmetry, G mean you go to the some omega 3, then we can move to the Einstein plane, and this gives the same Strobanski model from the coupling between Higgs and the Riemann curvature tensor. Also, there is the R-square impulsion, other type of the scalar tensor theory with the modifications of the gravity, the R. In this case, the R-square terms included, and after the conformal transformation, namely, we can obtain the type of the Strobanski potential form. The other possible form for the Strobanski impulsion is alpha attracted. From the supergravities of the SUSY, there is a non-trivial GR, and this makes the pole in the kinetic term. We talked about this in the previous some videos about the supergravity model. So this after the transformation, namely the Strobanski potential can be realized, or the T model, like the tangent hypertangent potential form can be generated, which also helps the flatness of the potential. The other possible impulsion model, like the K impulsion, the kinetically driven impulsion, and the worm impulsion, the impulsions generated from the subdominant thermal mass. And the old impulsion, pi that not oscillated. This is on the metastable vacuum. Paulus impulsion, exponential to this form, but this is excluded due to the large post-spectrum index. And the Basturol impulsion, eta is not small to the 1. The thermal impulsion, the phase transition effects that are included. The thermal effects changes the potential form. And ultra slow roll impulsion, the potential is too flat, so there is no slow roll. And the stochastic impulsion, the statistical random noise becomes the dominant and this induced impulsion. And internal impulsions, which is the impulsions does not answer about due to the quantum effect. So there we talk about the several forms of the impulsion model. Some of the largely excluded by the observation. There are several types, and we first talk about the chaotic impulsion as a super Planckian model, and there are other models like as some natural impulsion, Hill-type one, and hybrid one, and the many well-known modern examples is the generalized Strobanski with the exponential form. The example of the Higgs impulsion, R-squares, and alpha attracted thing.